So if any of you went to Mobicon last year, you might have seen some of those slides, because some of it is actually based on the topic slide last year, and it's just easier to pull existing slide that were better made than making things from scratch. But in some sense, I actually started this project by accident because one of my interns wanted to do something different, and then I just said, okay, why don't we just repeat what people have done first and see what's happening, and then we start to run into issues, and then we start to see there's actually lots of interesting things there. So, I'm not going to tell the story in the same way, but hopefully it's interesting at least to you as well. So, of course, usually I start with some kind of trends, and I'm sure everyone here will know about these things. Basically, mobile devices are taking over the world. Lots of phones, tablets, and nowadays people have been talking about wearables for a long time. But I would say really it's starting to really happen now with Google Glasses and other gadgets like smartwatch, whatever. And so some of the dates here, as you can see, is a bit old, and the point is to show you that actually has been happening for some time. We often don't realize that, but when you dig up these sources, you actually know just to what extent these things have been growing. And as a result here, so we tend to expect more and more rich interactions. So I don't just mean the typical user interface thing people talk about, but just kind of, how do you make devices to really help you, make use of something, interact with the environment. And especially, one thing that I actually noticed is that camera is actually a major thing here. So for example, barcodes you have seen, and also augmented reality stuff traditionally was somewhat related to camera. Now how you invoke it depends on what you do, but that's somewhat always related. So this is also what we were sort of thinking about, and actually, I'm sure you've been to talks and conferences where people take pictures of the slides as a more, manual way of recording things. So that's actually becoming more and more useful as information receiver kind of medium. So okay, I talked about barcodes, and I'm sure you've seen barcodes everywhere as well. And in fact, in some sense, I actually think in different places they are used to more extent. So here I've actually got a few different examples. So the first one is a clip from about 2 years ago where on BBC actually they said Gibraltar was doing something. So the idea was that they want to, so in Gibraltar, there are lots of tourist attractions, so probably some monuments, some whatever interesting. So the idea was that they would put some kind of barcode next to each monument. Now maybe on wall, maybe on something, I'm not sure. And if you scan that barcode, it will take you to a Wikipedia page based on this barcode, based on this monument or whatever it is. So I guess they were thinking it would be helpful for tourists to get to know more about, ultimately discover what they are seeing and get a better experience of for tourists and whatever. Now, I actually haven't been able to follow up to see what's happening because I tried to Google back, I didn't see any more updates on that, so it'd be interesting to see what's happening. So here, I think this is actually a screenshot of a TV in China. Of course, I got the image online, but that's where it came from. So, in fact, if you go to, I think some of the Chinese students here, or you might know, if you go to a website like Taobao, you see barcodes everywhere. They pretty much tag almost every item for sale with some barcodes. The idea that you can scan, you can get things more quickly, and hopefully that will help them get more sale that way. But the thing with this here is actually even on TV screens, you're starting to see things of this kind, which you may not expect originally, but that's actually happening a lot. And then the other example was actually a picture I took in Microsoft building when I was still there. That's why it's big out, because it's actually in a dim lit area next to the elevators. But also, when it was just kind of starting point when people put up something, they actually put a barcode there. It seems so natural. And of course, there are many more examples here. I'm not going to explain what they are because I don't know. I just took them from the website just to show they're being used in a variety of ways, very innovative ways as well. Sometimes different surfaces, different size, distance, whatever. So it's actually becoming very you see everywhere. Maybe not to this extent in the same, but actually certainly in China or some other countries, you actually see them a lot. So I'm sure. Oh, this is when I say this is the isoid which is big.
Oh, the spectrum.
This is supposed to be square, but it looks very much squashed. Anyway, so I'm sure most of you know what happens when you see a barcode like that. You scan it with your phone, and then typically it will be decoded into a URL. So the idea, I realized that the original idea for having something like this was that you'll be linking a physical object with some kind of online presence with more information and something. So in this particular case, And if you have additional Wi-Fi or cellular or whatever connectivity, then you get what's on that link. So in this particular case, it's actually something about Windows Phone. Now, but actually, like I said, nowadays barcodes are being used in many more innovative ways. So it can be a lot more than URLs. There's a simple example using, you can encode in your contact information in barcodes. So if anyone here has used WeChat or know about WeChat, which is very popular online social network in China or with Chinese people, you can just include your contact information and the other guys then scan it and you can automatically get startup things, which makes it much easier. Or like I said, part of the reason I showed this picture was that it's on a TV screen anyway, so you might as well show a video, right? And you can actually transmit a lot more information than just a URL. And the advantage there is, say, if you're a tourist in Gibraltar or somewhere else that's not where you are, you may not have additional access anyway. So having something that's self-contained will be actually a lot more helpful. And the interesting point is, sometimes because it's attached with physical objects, they can give you a better contextual awareness in terms of location-based something. Maybe if you want to see a movie nearby, you want to know where the nearest movie theater is, or some kind of these kind of contextual aware applications. Now, okay, that's the background story. So usually then we start to get into more technical stuff and talk about challenges. Of course, there are lots of here. They are roughly color-coded here because I'm not going to deal with all of them. The first two, as you can see, is something that I'm going to address a bit more in this talk. And there are other general issues about when you're trying to decode something using camera, there's issues from how do you handle hardware, how do you handle basic signal, and when it's on the phones, there are computational issues and in seconds, whatever. But going back to the first point, so if you think more about this scenario, right? Typically what you see is you have a screen or some display or whatever, which acts as a universal transmitter. And then you have cameras, whether it's, it could actually be an SLR if you somehow connect that to some computational thing to process those images. But you have phone, everyone has different phones, different devices. It's actually very diverse. So diversity in terms of what the hardware can do. And they can be doing this anywhere, right? So for example, if I see this screen here, I might be standing here trying to take a picture here, and anyone sitting over that corner might be doing that. So essentially, from a communication point of view, this is just a broadcast channel, and you have a lot of diverse, and all this hardware capability, you can also translate that back into some kind of channel condition as well. So effectively, you have very heterogeneous channels, and so for communication point of view, one of the classical issues, if you have a broadcast channel, what do you do there? I mean, conventionally, you are constrained by the worst guy there, right? Because you have to make sure everyone gets something. Now, depending on what you do, the worst guy probably is the main guy who tell you what you can get. So the issue here is, what's happening here, right? Can you do something interesting? So I listed 2 points, but essentially they actually still about the same thing, but just they are referring different points here, different ways here. So in the rest of the talk, I'm going to talk about 2 pieces of work we've done. LightSync did come first because we went into that issue first, but also that it helps me to explain some of the issues in the temporal domain, and then I'll explain the spatial domain a bit more. And they're essentially still kind of similar issues, so I'll explain a bit more what the issues are and how we try to address these issues. Not the best solution, but one way to do it. Okay, actually. Anyway, so for synchronization, the issue really comes from how the frame rates match on both sides. So your display, so you play a video, for example, right? There's certain playback rate. Now, typically, we are more familiar with, because video is typically done in a standardized way. So we're familiar with 30 frames per second playback rate, and it's actually very steady. So steady in the sense of stable, steady, in the sense that you can control more easily, and it's more standardized and whatever. So typically, what you see there is, okay, it's high rate and steady. Now, on the device side, as I sort of mentioned a little bit, you have different hardware, so they might be better or worse. So so at the time of this, actually I should have changed that. So at the time this slide was done, the 15 to 30 frames per second was the most common one. Actually, since last year, iPhone 5s can actually achieve 120 frames per second. So, but that's pretty much the only one that's so far. Everyone else is pretty much still in the same range. So they can do, and of course, because that depends on the hardware capability and something happening there. So that's a hardware itself. But also the reason there's a range of frame rates is also because you have different lighting conditions. So if you want your image quality to be good enough, you need to get enough light in order to get something sensible. And that's also a condition for why sometimes you don't want to run it at very high frame rate anyway. So for example, if you fix something in the firmware, you can always say, okay, whatever happens, as long as the hardware doesn't burn, you can always give me an image as a frame setter. But that may not be anything useful, right? So that's lighting issue in that case. And of course, because we're talking about phones a lot or something that has additional system factors, sometimes there are interrupts somewhere else in the system which can actually interfere with what the camera is doing. Or maybe the camera is actually sensing fast enough, but it's not processed fast enough, which again, there are some unintended consequences. So again, some of these issues are not inherent, but it's just the way it's being done. But then if you want to use these kind of devices as it is, then there are all these issues all becoming part of the big picture. So basically, these two sides don't quite match up. And as a result, when you see, so basically when you have the display some camera like this, you see a bunch of different frame patterns. So here we made a custom video. What happens here is in each frame, there's just one vertical bar, and it moves to one block to the right in each successive frame. So essentially, you can tell that based on which bar you see, you pretty much know which frame it is in the whole sequence. I think it's roughly 30 frames per second. 30 frames in this sequence. Now, so we might just get one single frame, like I said. If you see one bar, you know where it is. Notice that it's a bit grayer because typically there's some kind of contrast or whatever. That's what happens. That's good, but you might also see that. So I think you can see it. So here you can see there's actually bits of 2 frames there because you can see 2 bars. Now, if we zoom in a little more, actually, the patterns mix, change by line. You might not know about this, but anyway, I'm just continuing go through them. So when I say this mixing pattern changes, it also implies you might have different numbers of frame components there. So for example, at the top, maybe there's actually just the first frame, and really somewhere in between you get both frames, and then by the time you get to the bottom line, it's mostly the second frame. That's actually quite possible. The reason you see this is actually something called rolling shutter, because typical cameras, there are two common types of camera sensor. You guys actually really know that. CMOS or CCD. CMOS is the most common one for phones and mobile devices because it has a low energy footprint. But the thing there is, you actually scan the thing one at a time, which means that when you see an image, the line at the top is not scanned at the same time as the line at the bottom. So the camera might be seeing different things altogether. Just to show an example that makes it actually even clearer. So here too, let's say we have 2 successive frames, which are alternating grades to just one offset. And then if somehow you play them successively and try to take an image of that, if the rate is not quite right, you actually see something like that. So you can see at some point it's transiting to the next frame. Okay. All right. So go back to the frame pattern now. Of course, there are reasons why there are 2 lines here. There are actually more interesting patterns there. So without 2 frames mixes, you also can get 3 frames. So this one here is actually a bit faint, but there is a little bit of a thing there. Unfortunately, these are, I get whatever I get, so I cannot control how they look, but you actually do see these kind of things happening. This is just a more elaborate version of the 2-frame mixture that you can see pretty common. And then there's another interesting case. So here, you see 2 frames. They are actually successive frames that you record. But if you look carefully, that bar, remember I said each bar corresponds to a particular frame. That bar is actually missing in both frames. And given that these are actually successively recorded frames, this means that we actually somehow skipped a frame on the transmit side. We just lost it for whatever reason. Now I know why it might happen, but so if we look back at, just try to put this all different pattern in perspective, right? So for example, let's say we have some kind of camera capture rate, and then there's a range of display rate we might run into. Then what typically happens is that if your display rate is up to half of the camera rate, then you get pretty much alternating frames of a single frame and a 2-frame mix. Actually, if your time is very well, you might just get a single frame, but quite often there's going to be a phase offset, so that's why you get the mixed frame. This is somewhat in line with Nyquist's theorem about sampling and stuff. And then once you get up above the half rate, whatever, then you start to get pretty much all frames will be mixture of 2 frames. Again, in this case, in theory, if you get the phase offset right, they could still be single frames, but in practice, it almost never happens. So essentially, you get 2 frames mixed kind of all the time. Then if you keep going further, then this is where you start to see from 2 frames to see 3 frames. And occasionally you actually miss a frame sometimes. Now where you miss it depends a bit on the system, what the system is doing as well. And going further, you get, similarly, you start from 3 frame mixes, maybe even 4 frames mixed together, and then occasionally miss something. Okay, so like I said earlier, so traditionally we can only decode this pattern, right? So this is where there's all this talk about we want to synchronize frame, and this notion of frame synchronization comes from, because we only know how to do, decode when there's the right information there. But if you think about it, right, look at this part, for example. There's actually a lot of information in these frames, and we get a lot of frames of this kind. So it's actually a waste if we just don't do anything about them. But usually you can't do anything about them, right? And as a result, normally if you try to synchronize frames, whatever, you really are not using a huge part of the spectrum there. You're also constrained by the camera. And then if you have, like I said at the beginning, if you have a bunch of cameras, they have different capabilities, then you are constrained by the worst camera. Okay. So in some cases, it's kind of inefficient. Now, if we want to flip that, then essentially we want to try to achieve some kind of asynchronous communication. Or, whether it's called it's more technology, but essentially we want to try to make use the other side of the spectrum. And the goal here is that within this range that we looked at, that's very common for common rates for transmitters or receivers, then we want it to work with any of these combinations. Beyond that, we can't generalize forever, but at least within this range, it should all work. So basically, this requires 2 things. Now, first of all, like I said, we get lots of mixed frames, so we need to have some way of figuring out what to do with them. How do you get information from them? And then, like I said, occasionally we do miss something. It may be a whole frame, it may be parts of a frame. You actually see some. That's actually more common. You actually skip a few lines rather than the whole frame. And we want to somehow figure out how to get that back. Otherwise, you don't have the complete information. So, the first part I will talk about, called LightSync, essentially will do both of these things. So for the first one, basically what we do is try to have some kind of color tracking within a frame for each line, so you can really figure out what's actually happening, what frames are mixed together, and then you can unload it to the mixing. Then for the second part, it's just some kind of erasure coding, which is again somewhat considered a technique in communications, but it actually applies very naturally here. Now, the interesting is, really if you look at these 2 things together, what we have really is some kind of interframe coding. So typical barcode design, whatever, really is an intraframe code. You figure out how you lay out whatever things within the frame. But what we're saying is, give us that base code, we do something across the frame, and then that should give you this basically what's happening here. Now, that's not going to work with any barcode, but typical barcode with like block base, and that's all going to work. And monoframe is useful because that's the thing here. So I need to do a quick demo. Just playing with it, but why is it not? Okay, so let me first quickly explain what's happening, because for some reason, no, that's the estimation is wrong again. What's the? Let me see if that works. So, okay, yeah, that should. So, for some reason, the video was originally recorded in Windows movie format and then played fine, but somehow when I play this on the Mac, it seems to be played faster than I recorded it. So let me explain a little bit what's happening, just in case it zooms up so fast. So basically, my intern was trying to encode the file into a barcode video, and then he will try to play it first at the same rate as the phone, and then faster than the phone, and then you'll see in both cases, he can actually record the video still and then decode the information on that thing. Okay. So here he's trying to encode some text message. And that window shows you some parameters of that video. So this is the end video that encodes that text. The text was actually the abstract of our paper. So this is basically, he got that. Now he's going to try to increase the rate to 25 frames. The phone is actually receiving at 20 frames per second. Basically, that just shows you it works. Okay.
So do you have some redundancy in the code, right?
Yeah, there is.
Do you think this could also work without any redundancy if the screen is faster than the phone itself?
If you want everything, that's not going to work, right? From information theoretic point.
So the reason you can run faster is because you have some redundancy.
Yeah, essentially. So, but this is why you'll see in the second part. That's why we did the second part, because that's one reason. That there's one constraint for that. And basically, it's like because of the efficiency theoretical limits, you can't get everything right. So, okay, so that's the demo.
Sorry, the redundancy is spread over temporarily. That is multiple frames.
You'll see later how it's done. Basically, just being. Redundancy is just being played again. That's the inherent redundancy, but not just the repetition coding.
Yeah. That was my doubt.
The second part. So okay. So
I'm sorry. Did you say that the barcode is looping?
Yeah.
So within the time he held the phone there, it actually repeated several times.
Yeah. Because I'll get to that point a bit later, because that actually also corresponds to one type of scenario where when you get some information, it is being displayed in regular fashion anyway. So this is where you can just get whatever, you just take however you need.
Right.
That's why we have a scale with the receiver side and transmitter side. Okay, anyway, so that gives you some idea of what this thing actually did. So now I'm going to talk about the actual techniques. So first of all, like I said, there are two parts. We need to figure out how to decode mixed frames. So let's first look at the mixing patterns, right? Now, like I said, in that range we looked at, basically we get up to 3 frames mixing. Now, this basically boils down to you have 3 blocks mixed together, right? So again, typically, because like I said, we typically deal with monochrome, so you have white or black as a base color, and then there are just 8 different possibilities, really. We have 3 blocks mixed together. So then when you get something that's kind of gray, you just want to figure out which 3 blocks give you that gray color, kind of. So let's look at all these 8 cases. Now, okay, actually, no. So, okay, let's say you get a bunch of different frames and you see different gray colors, right? So first of all, this case is easy because if it's all black or white, pretty much you get black or white. Now, it's not going to be exactly, so let's say even if your black is say 0 or white is 2055, you're not going to get exactly that numbers when you receive them, but it's going to be close enough to those edges, to those ends. So you can pretty much say, okay, at this point it's going to be white, and it's pretty much because it's all white from from the base frames, and similar for black. And then there are also 2 interesting indicators. So it turns out when you have these frames mixed together, at least if you have LCD kind of displays, then the mixture, the weight of the mixture, the mixture is really some kind of linear combination of these 3 frames, and the weight is roughly the time each frame is shown during the whole exposure time. Now I'm saying this is approximated because there are different compositions for white and black, and so it's actually not exactly linear. But approximately this is actually pretty much true. Now what this means is that when you have 3 frames mixed together, the middle one roughly takes about 50% of the weights, and the first and with the other half split between the first and third frames. So then, if the first and third frames of the blocks for those frames have the same color, then roughly you always get about 50-50 black, white in all cases. So you pretty much see, roughly median stage rate. Now again, like I said, this is slightly approximate, but within slight, lags or whatever, it's pretty much true. So again, basically when you see this gray, you roughly know it's either black, white, black, or white, black, black, white, black, white. Now you don't know which one it is. So that needs additional method to disambiguate, but it's roughly one of the two. Okay, so then we are left with formal cases. That's actually trickier because, like I said, the results will be linear combinations, and they can be any time. The proportion of each can be any. So you can basically get a range of gray colors from all these mixtures. So for those, we actually have to track them. There is actually a better way to do it otherwise. So basically what we've done is, let's say we have, so here's a schematic of frame layout. It doesn't need to be precisely like this, but this is how we've done it. Just say you have some kind of corner borders to help you locate the barcode. And then we play 4 vertical tracking bars next to all these frames. Sorry, next to the data areas. Such that if you look at each line, you actually follow the tracking blocks. So this does per line tracking of them. The only thing is, basically this shows you the relative position. So say even if your barcode is has a portrait kind of orientation, that's fine too, as long as you make sure the barcode is vertical, perpendicular to the scanning direction, and then that they have to somehow make sure you can track each line. And then we have some kind of encoding patterns to make sure.
Can you say again what exactly the tracking bars do for you? So the orientation you can also get from the corners.
No. So I'm just saying the tracking bar, it's actually here kind of. So we're putting some training blocks in some sense, and then the training blocks will help us decode. So the way we're putting training blocks is basically putting some kind of encoding patterns here.
Oh, the tracking bars will also change color over time.
Yeah. So what happens? So like I said, here I put out one line, right? So you see 4 blocks on that line. Now they correspond to 4 blocks in each line here, roughly. So here I'm showing, say, for example, say if you have 4 successive display frames, and then here's one line of those things. What happens is that we make them following some kind of alternating black and white colors. So here you notice it's actually repeating every 4 frames and shifting by 1 each time. So the result is that, so if you look at these patterns, what happens, and so like I said, so this is the full reference block, and together they form reference bars, I sort of showed you again. And then, so when you have, anytime you have 3 frames mixed together, now if you look carefully, we have 4 different combinations here, right? The same thing applies if it's next 3 frames mixed together. So this is actually the 4 cases we talked about that were tricky, and we couldn't really have generic ways to figure out what they are. So this is why you need to sort of track. And when you see, so for example, when you see a bunch of colors like that, you can actually compare your data block with one of these to see which one is the best match, and that gives you basically some idea of which one of these was, where it came from. So, just to give you some indication of why this actually works, if you're more familiar with information theory and stuff, like in some sense we're doing under something, right? So usually it's not supposed to work, but it does work in this case because there's actually a lot of sparsity there. So as I said, we are really dealing with a small number of cases of blocks mixed together. So we don't need to figure out, so there are only a certain number of combinations that may come up within this mixing. So if you look at the whole color spectrum, we only need to pick out a few points. This is kind of like when you do modulation, you're not using the entire constellation space. So if you only need to pick out a few points, you can actually disambiguate try to lock any signal to a nearby position and figure out which one it corresponds to. It's kind of similar concept here. Okay, so this actually goes back to your questions earlier. So also dealt with how we can decode things. Now when there are occasionally lost frames, we want to recover that. And also for the tracking bar stuff, it's not going to give you answers completely. I mean, sometimes there's still ambiguity. Because bottom line is, sometimes different patterns do give you the same color. There's nothing else you can do unless you have additional information. So this is also partly going to help. And we did something very simple here that seems to work well enough, and there are some other inherent limits. Basically, we take frames, when there are a bunch of frames, right? We take 3 frames as a group, and then just generate pairwise XOR of those frames as basic encoding frames. And then we just do a looping display. So the first batch is just the same frames, and then we have those encoding frames, and then repeat continuously. So it's actually a very simple mechanism. Now, the reason we use 3 frames as a group was because we observed that it's actually very rare to have 3 consecutive lost frames. And the fewer frames you code together, the faster it is going to be when you do decoding. And the bottom line is, unless you encode all frames together, encoding 3 or 4 frames together give you about the same property in terms of decoding efficiency or whatever. I mean, in terms of how well you can guard against lost frame until the next iteration, eventually, essentially. So, but they have different computational costs in terms of decoding. So in that case, the fewer frames you put together, the better. And we use MIMO, which is 2.
Any specific reason you're using these colors, or?
I'm just illustrating.
Illustrating.
Yeah. They are different packets. So I'm just showing there are 2. We have pairwise 2 frames included together. Okay. So let's have performance. We implement that both in the offline mode and online mode. So here, this is actually the same screenshot of the same map you saw in the demo, where this 20 frames per second here shows you this phone is actually capturing at 20 frames per second. And then the numbers at the top is showing the perceived interframe interval for when the app is actually hitting that. As you can tell, sometimes it's very small, sometimes it's actually not. There's actually a bit of variance for probably more of a system reason than just the sensor itself. And then for performance, just to remind you, our goal was actually to make sure it does work within any of these coverage. So this is actually the main thing we look at. And because of that, we're actually looking at the effective frame capture rate. Not so much the throughput, because throughput depends on how much you have in each frame as well, which we can adapt, and that's not something we changed anything much anyway. So just to give some idea of what we should expect, to get. If you have a phone camera like that, as I showed you, and then say if you want to plot how the effective capture rate should vary with the display frame rate as things go, then ideally you want to see something of this kind, right? I mean, if the display rate is low, then it grows as you play faster. And then at some point, once it's faster than the capture rate, then you can't get it better. So this will be the ideal case. Now, typically, so I'm saying this. But conventionally, when you do synchronized communication, it's actually a lot more limited. So here, actually, when I draw this slide, I'm a little harsh there because you kind of expect this to peak at about half the rate and drop to 0. Now, in practice, it's not going to be going to drop to 0 immediately or exactly, because it depends on how you count what's decodable, and for example, do you count partial frames, do you count whatever. Because if you have only a little bit frame mixed together, you can still treat that as just noise and then decode things. But at least for the most part, this is the kind of behavior you will see, even though it's not exactly immediate 0. And what we've done with LightSync is roughly we get to something of this kind. Now again, we do see a little drop off because it's not going to decode everything perfectly. But for the most part, we actually do pretty well for a large part of the thing here. So yeah, we do get to that peak. We certainly do get to that peak for sure. We just lose a little bit on the further end because there is a cost always when you try to do something that you are not supposed to do. Okay, so we tried a bunch of different phones. Lumia 920 at the time was the best phone we had, and it captures as a frame status. So you see pretty much it just goes up. 25, 27 is very similar anyway. And then for the phone that you saw in that screenshot, this is what happened. It does go up, drop a little bit. It dropped. It didn't quite go up to 20, but it's pretty close. It's more like 18 or something. But given the rounding error, it's much pretty close. We also had a more wimpy one, which could capture 15 frames per second. So that's roughly, it actually takes a bit more cost at the high end, but you still get to, I think it got to about 14 or so at the top. In fact, so actually the demo version you saw has slightly better decoding, so the lines actually go up a little bit, and also the variance is slightly smaller, but we didn't actually have the exact remade lines here, so I'm still showing slightly older results, but the trend is pretty much the same. So basically, this is what we wanted to do. We wanted to work with all this range of frame rate combinations. We got that, and then the goal was really that the performance will actually scale with a receiver capability, and that's also what we managed to do as well. But of course, like you said, like Michael said earlier, one of the things here is you need to have redundancy at either end. So if you want to have everything, if the display is really playing things faster than you can get, and if you then get again, the best thing you can do is just not get all of it, right? So then after this, we saw, can we actually look at it in a different way? So for example, in this case, if things are faster, being played faster, or larger, or whatever, then can we just decode part of it, not the whole thing? So because that's another way to look at this picture. Because basically, either you want everything, but just make it more scale on, just move the bottleneck, or somehow make it more flexible, and then just different ways of adaptation. So this is part of the why it was very natural to look at another way to look at this code design, and this is going to come up in what we come in a month. So we call this Strata. It's kind of layered coding. Now, Strata itself means lots of layers in the whatever atmosphere or rock or something. It kind of fits with our goal. So switching gear to Strata. Now, again, I showed you these pictures, and there's a reason why I chose this picture, because you can see these are different sizes, different scenarios. So, for example, if you have a big wall like that, sometimes you might be too close. Sometimes you might be, or with a poster, you might be too far away. So quite often, you might not get all of it. Now, if you think about it, right? Typically, what happens for existing code is that you have to capture all of it, otherwise you don't get anything. Now, there are two parts to all of it. So one is, so here from a schematically, let's say your camera view, your code has to be completed within your camera view. That's easy to understand, right? Because otherwise you cannot have everything in that frame. But also, let's say if you have like the minimum code block is about that size, in that circle, then your capture image has to at least have that resolution. Otherwise, you cannot figure out what's the code block. So basically, you have to have that. Otherwise, you don't get anything. Now, if you have more resolution than needed, that's fine, but you don't get more from it either. So this is that's why we say this has some kind of all the same behavior, which can be a constraint, whereas it's not as flexible when you have, again, lots of diversity in many different ways. But if you think about it, when we want to send information, whatever it is, quite often, naturally, there are multiple resolutions, right? Now, so here, this is our tool example. We actually made this sign just to show what you can do. So for this one, if the focus at back, you might just see it's more of a prominent M shape. But of course, you can read what's inside as well. Now, but if you think about the kind of adverts or billboards, whatever you see something of this type as well. So for example, you have fonts of different sizes, right? Different colors just to highlight different parts of it. Or the reason, say you go to a Wikipedia page, there's usually a summary at the top and then the full page. It's pretty much for the same kind of purpose, so that you can get part of it to get the gist of it, and then if you want more information or if you can or whatever, you can see more. Now, how many granularities depends on your application, but basically having a choice, having an option for multiple granularity is something is kind of useful. But this is again, this is the information side. Now, So I keep talking about different cameras can do different things. So for here, we have a bunch of different cameras. Like Lumia 1020 has, it's a very high res camera. And then I think HT's design is actually the worst one for this one. Basically, if you have the same code image, right, displayed somewhere, I forget how big the version is, but it didn't matter here. And you try to take a picture of that code, that block, basically a square block, at different distances with different cameras. And these are the y-axis here, basically plots the side length in measuring pixels of the thing. So, I mean, precisely where they are doesn't matter so much. The point here is, really, if you look at the best cameras, they can get much more detailed image at the same distance than another camera, essentially. So for example, sometimes when you can't see anything, say with a small camera at 9 meters, you can still see a lot more with say Lumia 1020 or Note 3 is also a good one. Okay, so basically that already said you have essentially multiple resolution on the display side and also multiple resolution on the receiver side. So somehow, we need multiple polarities. And the other thing is to note is that when you have cameras that, say, if your camera is too far away, that you get a very low resolution image. What you get is actually something on it. So here, let's say this is the original image you have on the screen. Again, it should be square, but anyway, you see what I mean. But then if you capture the same thing, I think this was captured on Nexus 5 at roughly, say, 30 meters away. And of course, the actual image will be tiny, but if you enlarge it, this is what you will see. Everything becomes mixed together. So this is actually the main challenge here, because okay, you have multiple resolution, then of course you want to somehow match them up. But basically, as long as it's not completely matched, you get mixing of this kind, and you need to figure out a way to address this mixing spatially so that you can actually do any decoding. Now, if you think back to what I said in the kind of LightSync, the temporal when your frame rate capture rate is slower than the display rate, you get temporal mixing. It's actually somewhat similar here. Only that in this case you get more. You could have more control depending on how you lay out the pixel. Whereas that depends a lot on what the camera is doing, and you don't have as much control there. But essentially, the mixing I showed you earlier is actually have really the same nature, which is why the kind of goal we want to apply here actually extend very naturally to the temporal domain as well. Even though for the most part I'm going to talk about spatial here because it's easier to show visually. So okay, so this is why we were trying to build Strata. Just to recap, so we have multi-resolution. We want to have a support multi-resolution encoding. Now, if you are familiar with communications, there are things called hierarchical modulation for typical channel coding, which is that you can actually decode any part of the constellation, and then if a channel is good enough, you decode more. And then for source coding, I imagine some of you have heard of scalable video coding, somewhat similar concepts as well, but just done in a different way, in the sense that if your rate is high enough, you get all of it. If not, you get some base in it, so that it can be more adaptable, more flexible. So this is the intuition for us as well. I mean, kind of analogy, we're not going to use the same contrast, but we want to achieve somehow some effects. And of course, when you have this kind of encoding scheme, it's important to figure out how you decode to match up with them. And this is where all this spatial mixing and stuff becomes important to handle. And the goal then, once you can handle that, you can actually really support all this diversity and that stuff. So the design is I'm just going to give a simple intuition that should be hopefully easy to understand. So, of course, hierarchical modulation, if you know about it, is that you separate your code into different layers, right? So that you can decode part of it. Now, when you see an image like this, for example, right? For the most part, it looks black to you, I'm sure, or at least I hope so. So imagine if this is only one block or indicating one bit, then this will mean black. But if you look closer, of course, there are individual smaller blocks. Some of these are actually white. So this is a basic way of saying, okay, how you can have two layers, right? So essentially, the main thing here is that the white is actually interference, or the smaller blocks can interfere with the bigger block. You could actually make it actually the other way around, but this way is actually more natural. So the white is going to interfere with the black in the bigger block. So the key here is that if you want to do anything to make sure both the bigger block is recognizable in the right way, and the smaller block can be recognized as long as you have the right dimension there. the key really is to control how many white blocks there are in this thing. Okay, so this is the intro. I mean, it's a bit texty because usually I try to use pictures, but this one I still need to think about how to make pictures of this. The basic idea is when you have layered codings, you can have code blocks of different sizes which correspond to different resolution to support different layers. Now, for temporal domain, that basically means you can have different frame rates, right? Because the resolution is the interframe gap, and you can have, typically it's going to be uniform, but there's no reason why you cannot do that, when you can do something different. So if you can control the interframe gap to adjust just how many frames you want to pack together and to achieve different granular difference. And then for between say, think about two adjacent layers, right? If you want to make sure both layers are decodable, you just need to adjust the proportion of these different colors, which are interference for the other layer, to make sure it doesn't affect the other one. And then if you want to extend this to more layers, a simple way is to do this recursively. So for example, if you know how to do it for two adjacent layers, then you can divide the smaller block in the same way, and then apply the same two-layer thing to that small block, and then this will keep going until you get to the individual pixels, or you cannot divide further in terms of frame rate, whatever. That's the kind of intuition. So what we've done is, so to adjust the proportion of colors, basically we have this notion of control block, the reserve block. You can think, especially it's easy to visualize in terms of reserve block, but in terms of temporally, you can think of it as a reserve frame interval. It's actually the same kind of common notion anyway. So here, for example, if you look at this simple example is 4 base layer blocks. So the green outline shows you roughly how big a base layer block is. Say we have 4 blocks here, correspond to 4 bits. And then the smaller green circle show you how big the smaller block for the smaller enhancement layer is. We call this base layer enhancement layer following the terminology in say HM or SVC kind of hierarchical coding. So here you notice in that green thing outline in green, the reserve block is a majority, takes up the majority space. And by reserving that much space, you are going to, so if your decoding mechanism is like you count the number of black and white pixels, then this thing should look white to you, regardless of how many black there are in the rest of it.
Like a parity bit.
Sorry?
It's like a parity bit in your packet.
Kind of, yeah. It's like we control the amount of noise that the black can generate to the rest of it.
It's a number of white and black pixels, not the intensity of it.
Yeah, it's number. Yeah, I mean we don't do anything to do with intensity right now. So now, of course, there's a price to pay as well, because if you reserve half of it, then you are not using the capacity of that half. That's there is unfortunately some trade-off there. So the next thing we do is can we actually get more capacity back? So here in this case, you've already seen that I have reserve block in 4 different shapes and orientations. So this 4 combination give you 2 more bits, right? So, okay, this is not a huge amount, but by trying to do little tricks like that, you can get some of it back. So that's the first point there. And then in practice, so the examples I showed you all have about half the space left. That's actually the safe limit. In practice, we can probably do with less. Now, how much less? We actually discussed a lot more in the paper about different ratios and factors, but simple way to put it is that if you have smaller blocks, then it's much easier to use a smaller portion as a reserve block. But there are also trade-offs of how small you want between successive layers and stuff. So in this case, basically, what we could also do is that, so if you reserve half of that as a reserve block, you can still use some of that for the third layer, where the blocks are going to be much smaller. They'll have much less effect on the overall first layer, but still you can get some more bits that way. So by constructing it that way, we can actually get more capacity back from reserving some of the portion of the pixels here. Okay. So this is basically we try to again put some bits back and then put together the whole thing. Hopefully that there's going to be we can sort of achieve a trade-off between distance or range of operation and capacity.
I was asking myself, how is this certainly different from just making the reserved block smaller?
So if your second layer is the same size of the third layer as the third layer, it's the same. But then so basically it's also every time, depending on how many layers you want to have, and what's the sort of, we call it ceiling size, like what's the ratio of block size between adjacent layers. It will determine how many more layers you can have and how quickly the capacity can grow. So there are different trade-offs here.
And the fact that you make the block size smaller, does it help in any way of making it appear white from a larger distance? Or is it only the number of blocks that matter, or the ratio of white blocks to black blocks that matters?
In practice, it matters slightly, but it's relative because you can affect actually, no. You mostly add bits to the third layer. You may add a little more noise to the first layer, but that's actually a lot smaller. If you implement properly, you can actually roughly control that. Because the point still is...
So the amount of noise you add would be different if you add the same size blocks as in the second layer?
You cannot add same... So basically, if you... I guess the way to add this is if you want to, depending on which layer you're adding. So for example, when you have 3 layers, you can add the third layer blocks to the first layer reserve block. If you have 4, then you can add the fourth layer blocks to both the second layer and the first layer, corresponding to the block size of those layers.
But in either case, it will add more noise to the...
It does, but then because the blocks are incrementally smaller as well, the die effect is also getting smaller. And the other thing is, so this is not explicitly accounted right now, but when you add blocks, they may be the same color as the reserve block anyway. So, okay, that really depends on your message input bit distribution. That is very hard to say generically because it depends a lot on that. But if you assume somewhat random distribution, somewhat half-half, then the amount of noise you're adding is also somewhat bounded. Right? Because even in this case, for example, the reserve block is actually white, and then the new data blocks you're adding are some white, some black. So you're not really adding it completely, but we're just reserving some kind of safe limit there.
Okay.
We're actually trying to look into to see if we can push this limit, and there are different trade-offs here. We're still calculating some of this. But basically, still the thing is, unless you know something about the messages, the bit distribution, there's not much you can do unless you other than being conservative about this. So for performance, again, it's very simple actually. I'm just going to give you a taste of what we wanted to do. So again, we wanted is that you can scale with capture resolution. What this means in a simple way is to say, okay, at different distances, or if you have different phones, then the number of bits or the number of layers you can decode correctly will be different. That's pretty simple to, you can kind of quantify, but qualitative, that's basically what we want to achieve. So this is an example image we had. Squashed anyway. It didn't have the local landing block on the side, but it's just to show you what the code might look like. There's no error correction there, so when we count the correct bits, we just count how many bits we can get from each layer. We don't worry about what happens if you add error correction or add some more redundancy within each layer. That stuff can be added very easily. So for the spatial performance for something of that kind, if you have a bunch of different cameras trying to scan this image at these different distances and count how many bits you can decode from all these layers, then this is something you see roughly. Higher bits is basically, again, the better the phone, you do get a lot more bits. The precise drop-off point depends a bit on where this phone is and which position, which layer is.
So the setup is you're displaying this, it's static, and you're...
Yeah, so this is just
the phone is fixed.
For example, this is where the image is displayed, and then let's say you are looking at say about, I don't know how long this is, but you are sending at these different positions, maybe 1 meter apart, and take a picture of that, see if you can decode, how many bits you can decode.
Is this a 2-layer code, or?
This is actually a 4-layer code, but the first layer is 1 bit, so there's not much there.
So the first layer is just the entire thing?
Yeah, yeah.
And second layer should then be?
I think so.
4 quadrants.
So
should be 4 quadrants here?
Yeah, no, second layer is actually 16 bits.
Oh, 16 quadrants.
So yeah, roughly, this is roughly how big second layer blocks are. I think something like this would be the third layer block, because they are not square right now, so somehow it looks a bit wrong to me. And then something of this size would be the fourth layer. And what's happening here? So
you also have 16 third layer blocks inside one of the second layer blocks.
Yeah, and we also have 16 fourth layer blocks inside third layer blocks. And I believe, although I can't tell just by looking at this right now, I think in this case, so we had third layer blocks in the first layer reserve blocks, and also fourth layer blocks in both the second and the first layer reserve blocks. So the capacity here is essentially about 2/3 of the, if you have everything just the size of this. Roughly 2/3, not exactly, but so we are losing about 1/3 of capacity, but actually it does give you a lot more flexibility. Actually, yeah. So this give you some idea of how many bits there are we can get. And then another way to perhaps a bit more intuitive to see is to see how many layers you can get. Now 4 layers is kind of no-brainer because the first layer is just 1 bit. But in this case, like I said, because we don't have any error correction, so when we determine how many layers can be decoded, we are so slightly relaxed. So for example, I think for this one, if we can decode correctly 97% of the bits of a layer, we will just say, okay, this layer, we have all this layer, because the rest can be easily corrected back from FEC or whatever. Otherwise, the little bit of noise is too huge. So here basically, you see that Lumia can decode more pretty much, especially at 5 meters and 50 meters. Whereas the iPhone 4 can decode only the third layer, even at 3 meters. So basically, this is a more intuitive way to show that's what we still have to achieve, and this actually can give us something.
On the camera side, the number of layers needs to be known.
No.
No.
You basically decode as much as you can. So you first detect the first layer, and then divide that because we have this division rule about how one layer, how the relative size of the blocks. So if you can decode first layer, then figure out then divide the blocks up to see if you can decode second layer. If you can, and if that's fine, then keep going. Now we can adjust that part, by according to some other rules, but the basic thing can be done easily.
And the verification of the decoding being correct.
So right now for experiment, because we didn't have error correction, so we do this offline. Like you decode something and then we compare this offline to the original image. But in practice, what you can do is just add some checksum. So for example, if you decode something, if the checksum is right, then you know it's right. So these are pretty standard in communication stuff. So we just don't bother. Actually, we play with different variants of this early on, but they didn't add much to what we need to know. So we are actually trying to do a demo, but basically in some live app, basically it will be based on that. So you need some error correction anyway, and then that can tell you, do I have the right message or not? And typically, there are 2 ways to stop. So either you get to a little pixel, you cannot divide the block further, then there's no more you can do. But more likely, if your error rate goes, if you use error correction and then your error rate goes down to some point, there's not much more you can get.
So, and this is decoding with one image frame, one camera image frame.
Yeah. So it's just I take a picture of that, try to decode. For temporary, the thing about so you can actually just basically command temporal spatial this way, as long as your temporal frame rate is low enough that your camera can process it. Because basically, like I said, the way we did for temporal is just control the frame rate gap, the interframe gap, and then when you get each frame, you can do the same thing as this one. So there's not much additional thing to do. I'm almost done. So just conclusion, basically, I told you about two things. They were called different names when they started, especially for the LightSync part, but really they are both about some kind of scalability, just in slightly different ways. Either you try to get everything, then you need to add redundancy and somehow load the bottleneck to the receiver, or make the information somewhat, more in pieces you can get public. Now, one thing I do have to say is the way Strata works, or even HM and SVC, you still get discrete levels. It would be nice if anytime you change slightly, you get something more. But that's actually a lot harder, and we don't know how to do that yet, but something we're thinking about. I don't know if that can be done, because I've tried that with video before, and I know it's actually quite hard to do. But there's something you can do, so we'll see. The basic thing is, so in some sense, I see these as kind of primitives for potential scenarios you can build on top of, for real applications. In some sense, what I'm showing you is somewhat abstract. That's true, but they do correspond to things like, if you want to show just the main, a short summary of, say, some kind of merchandise, and then the intrinsic consumer can get further information or something. Or another thing that, what some of the students often talk about is, say, quite often if you see something far away, you can get some idea what they are, and then if you're interested, you can go further to get more information. So there are different, so they can be potentially combined with some kind of interaction scenario as well. So there are potentially more interesting different ways of building apps or something as well. But as far as we're concerned for now, these are primitives for building these coding schemes for these kind of applications. Okay, so barcodes related work. I'm sure you know a lot of that. I'm not going to go into more detail. So just acknowledgements. Lots of students work on that. Actually, all the students listed here actually were undergrad at the time, and there are some collaborators. One from my professor, from college, the other was one of the team researchers. So we were talking about this. That's it. So I think I'm about right on time.
Thank you.